this module, you will learn about enthalpies of combustion and atomization. Combustion is a process of burning a chemical compound at high temperatures in presence of excess of oxygen or air. Combustion reactions are exothermic reactions. The energy released during these reactions is used to drive automobiles, ships, airplanes and trains, to operate industrial processes, rocketry, and for numerous other purposes. The energy change accompanying the process of combustion is called the enthalpy of combustion. It is defined as the amount of heat energy evolved when 1 mole of substance is completely burnt or oxidized in excess of air or oxygen, and is represented as delta CH. For example, when 1 mole of carbon is completely burnt, it releases 393.5 kilojoules of heat. The negative sign of enthalpy change indicates the exothermic nature of the reaction. The enthalpy of combustion is considered only if the substance oxidizes completely. For example, if carbon is oxidized to form carbon monoxide, then the heat of the reaction is minus 110.5 kilojoules per mole. Since carbon does not oxidize completely, the heat evolved during the reaction is not considered as the enthalpy of combustion. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion, with all the reactants and products being in their standard states at the specified temperature. It is represented by delta CH0. Combustion reactions release large amounts of energy. For example, 1 mole of butane on complete combustion produces minus 2,658 kilojoules per mole of energy. The energy released by the combustion of food or fuel is usually compared in terms of their combustion energy per gram, which is known as calorific value. Calorific value of food or fuel is defined as the amount of heat released by the complete combustion of 1 gram of fuel or food. Calorific value is usually expressed in kilojoules per gram or kilocalorie per gram. When 1 mole of glucose burns, it releases 2,820 kilojoules of heat. Hence, the calorific value of glucose is 2,820 divided by 180, which is equal to 15.67 kilojoules per gram. Now let's look at enthalpy of atomization. When 1 mole of a given substance dissociates into gaseous atoms, the enthalpy change accompanying the process is called the standard enthalpy of atomization. It is represented by delta AH0. Let's consider the atomization of dihydrogen into hydrogen atoms. In this reaction, hydrogen atoms are formed by breaking of HH bonds in dihydrogen. The conversion of 1 mole of hydrogen molecules into hydrogen atoms requires 435.5 kilojoules per mole of energy. Therefore, the enthalpy of atomization of dihydrogen is 435.5 kilojoules per mole. Now let's look at bond enthalpy. We know that chemical reactions involve the breaking and making of bonds. The breaking of bonds requires energy, while the making of bonds involves the release of energy. The enthalpy changes associated with chemical bonds are expressed in terms of bond dissociation enthalpy and mean bond enthalpy. Let us try to understand these terms with reference to diatomic and polyatomic molecules. In case of diatomic molecules, bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. For example, a 435.5 kJ per mole of energy is required to dissociate 1 mole of hydrogen gas into hydrogen atoms. Hence, the bond dissociation enthalpy of hydrogen is 435.5 kJ per mole. Note that this is the same as the enthalpy of atomization of hydrogen gas. For all diatomic molecules, bond dissociation enthalpy is the same as atomization enthalpy. In case of polyatomic molecules, bond dissociation enthalpy is different for different bonds within the same molecule. For example, the enthalpy of atomization of methane is 1665 kilojoules per mole. Although the 4 CH bonds are identical in terms of bond length and energy, the energy required to break individual CH bonds in each successive step is not the same. The energies required to break these bonds are successively plus 427, plus 439, plus 452, and plus 347 kilojoules per mole, respectively. The total energy required is plus 1665 kilojoules per mole. Hence, in such cases, we use the term mean bond enthalpy instead of bond dissociation enthalpy. Thus, mean CH bond enthalpy in methane is 416 kilojoules per mole. Bond enthalpies can be calculated using Hess's law. The knowledge of bond enthalpies helps us in predicting the enthalpy of a reaction in gas phase. The standard enthalpy of a reaction, delta RH naught, is equal to sigma bond enthalpies of reactants minus sigma bond enthalpies of products. It is important to remember that this relationship is approximate and valid only when all the reactants and products in the reaction are in gaseous state. You have now reached the end of this module. In this module, you learned that the enthalpy of combustion of a substance is defined as the heat energy evolved when 1 mole of substance is completely burnt or oxidized in oxygen. It is represented as delta CH naught. Standard enthalpy of combustion is defined as the enthalpy change per mole of a substance when it undergoes combustion, with all the reactants and products being in their standard states at the specified temperature. It is represented by delta CH naught. Calorific value is the amount of heat in calories or joules produced from complete combustion of 1 gram of fuel or food. Calorific value is usually expressed in kilojoules per gram or kilocalorie per gram. When 1 mole of a given substance dissociates into gaseous atoms, the enthalpy change accompanying the process is called enthalpy of atomization. It is represented by delta AH naught. Bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of a gaseous covalent compound is broken to form products in the gas phase. For all diatomic molecules, bond dissociation enthalpy is the same as atomization enthalpy.